Dear audience, hello, my name is Robin Chan. I'm a doctoral researcher at the University of Wuppertal, and I'm going to present a joint work together with Matthias Rottmann and my supervisor Hanno Gottschalk, both from the University of Wuppertal, and two industrial collaborators, Fabian Hüger and Peter Schlicht from Volkswagen Group Innovation. The title of this work is Controlled False Negative Reduction of Minority Classes in Semantic Segmentation, and as the title suggests, we want to focus on false negative errors. However, there are also false positive errors. And if you apply methods, in particular, if you apply post-processing methods like we do for reducing one of these error rates, it is likely that you will increase the other one at the same time. And we want to alleviate this effect with a method that I'm going to present in the following. We apply this method for the computer vision task of semantic segmentation, and we evaluate with respect to minority classes. These are classes that are rare in the data set in terms of frequency, and therefore potentially very important to detect. Without further ado, let's jump to the content of this talk. First of all, let me introduce semantic segmentation. Semantic segmentation is basically an image classification problem at pixel level. You can also view this task as clustering pixels in a camera image that belong to the same object class. And this is how it looks like. We've got an input image, we feed it through a neural network, and what we obtain is such a so-called segmentation mask. We assign each pixel to one color, and one color corresponds to one of predefined semantic classes. In this context, one connected component of pixels that share the same color, for example, this info sign here, is considered as a segment. And this is very important to remember in order to fully understand our proposed method. And for computer-assisted driving, it is crucial to have a comprehensive understanding and perception of the vehicle's surroundings. And in such a safety-critical application, semantic segmentation is a very desirable component. Semantic segmentation is a very high-dimensional problem, and this problem is still far away from being solved. So, with a certain probability, neural networks as statistical models that perform semantic segmentation will produce errors. And in general, there are two types of errors. Here on the left side illustrated is a type 1 error. In the original image, there's no kid standing on the street, but the prediction says there's a kid standing on the street. On the right side, we've got a type 2 error. Now there's a kid standing on the street in the original image, but the prediction says there's no kid standing on the street. And these two errors are also known as false positive and false negative error, respectively. And human intuition would suggest that in certain scenarios, especially in this situation, in this particular situation that we visualized here, it is more important to avoid type 2 errors. And that's why it is the main focus of our work. One way to adjust the sensitivity of neural networks towards predicting certain classes is via decision rules. And the standard decision rule is the maximum a posteriori probability principle, shorthand MAP principle. And let's go a bit more into detail. So with X, we denote the input data, with Y, the target, and with Py given X, we denote the softmax output produced by a neural network. And the predicted class is then obtained by applying the argmax function to the softmax output. So we simply choose the value, the highest value, or let's say probability in the softmax output after processing the data X. So in this way, one minimizes the chance of an incorrect class estimation. And from classical statistical decision theory, this is also known as the Bayes decision rule. And from decision theory, we also know that there are some alternative decision rules, like the maximum likelihood decision rule. And with that rule, we apply the argmax function to the conditional likelihood. This is different to the Bayes decision rule, where we applied the argmax function to the posterior probability, since X and Y are now interchanged. And with the Bayes theory, we can rewrite the conditional likelihood to this term here. And we maximize over all classes Y. Therefore, the location of the maximum is independent of Px. So what remains is the posterior probability divided by Py. Py is also known as the prior. And that's the only difference between the MAP principle and the maximum likelihood decision rule. And with the maximum likelihood decision rule, we choose the class with the largest conditional likelihoods. And that means we choose the class that fits best to the observed data X. And another view at this decision rule is that we have class weightings. So if we have a class that has a low prior, we divide the softmax output of that class by a small number. Therefore, we boost the sensitivity towards predicting that class compared to classes that have high priors. And at this point, it is very important to mention that this is different to arbitrarily assigning class weightings. And arbitrarily assigning class weightings would lead to ethical difficulties. But ML, the maximum likelihood decision rule, is another concept from theory, and it is very legitimate to use. And the prior probability that we need to apply this decision rule is approximated in a data-driven way. In our team, we developed a tool for semantic segmentation to quantify how reliable and trustworthy the neural network predictions are. And this is basically another model that can be added on top of the neural network that performs a prediction quality rating. And this task is performed based on dispersion measures, geometry, and location features. And it does the prediction quality rating in an automated fashion. And in this figure, we can see how it works. So on the left side, we see the prediction, the segmentation mask, and the underlying original image. And we observe that here, maybe inside that bus, there are some misplaced objects. And our tool that we term MetaSeg is able to detect such misclassifications, labeled as red here. Now, if we summarize the methods that are given, on the one hand, we've got the maximum likelihood decision rule that increased the sensitivity towards predicting certain classes. And it works particularly well for rare classes that appear less frequently in the data set. And we can view this one as false negative detection. On the other hand, we've got MetaSeg that performs a prediction quality rating. So this is a false positive detection. And the intuitive next step is to combine these methods. And we term this method MetaFusion. And the interesting question now is, how many false positive can we remove from the maximum likelihood mask by applying MetaSeg while keeping all additional true positives that we obtain by increasing the sensitivity towards predicting the rare class? We evaluate MetaFusion with respect to the human class and the cityscapes dataset. A preceding statistical analysis of the dataset showed us that this is the most underrepresented class in the whole dataset in terms of occurrence frequency. Therefore, the human class has the lowest prior among all cityscapes classes. And in the cityscapes dataset, which shows us different street scenes, this class is probably one of the most important classes, as overlooking such instances would lead to fatal consequences. The statistical analysis also showed us, if we compare the base segmentation mask with the maximum likelihood segmentation mask, that all by base predicted human segments lie inside a human segment predicted by maximum likelihood. And we make use of this relationship in MetaFusion. Now we need to choose the segments and the maximum likelihood segmentation mask that we want to further process. There are two cases. Either the decision rules agree or the decision rules disagree. We say that the decision rules agree if there is a non-empty intersection between a base human segment and a maximum likelihood human segment. We can also view this one as a confirmation for the presence of a human that base already has found. And the decision rules could also disagree. So there's no intersection between the base and the maximum likelihood mask. In this case, maximum likelihood suggests that there is a human that might be overlooked by base. And we can rewrite this one in a set notation. With K, we denote the pixels of a segment in a segmentation mask produced by applying the maximum likelihood rule after processing the image X. And with dx, we denote the set of segments for which the decision rules disagree. For MetaFusion, we constrain the set to only one class. In our case, it is the human class. So the C here in this notation corresponds to the class human. For the constructed set of segments, we apply MetaSeg. As a recall, MetaSeg is a method that is based on dispersion measures, geometry features, and location features. Therefore, we need to compute these features for each segment in the set dx given C, with C being the human class. We denote these features with a capital U for each segment K. And now we seek for a classifier F that distinguishes between a true positive and a false positive prediction. We say we've got a true positive prediction if at least one pixel of the segment matches the target class, and it is a false positive otherwise. We can also view this task as predicting whether the segment-wise IU is greater than 0 or equal to 0. In the end, we obtain a fused decision rule, in which we believe the maximum likelihood decision rule if our train classifier F says it is a true positive, and we stick to base otherwise. And the interesting result is that we get an improved trade-off between the error rates. In this plot, we can see the number of false negatives as a function of the number of false positives. As a baseline, we choose the base decision rule and the maximum likelihood decision rules. Furthermore, we add different decision thresholds that we get from applying priors with different degrees of interpolation between the base prior, which is essentially constant, and the maximum likelihood prior. And for each of these thresholds, we apply MetaFusion. So that point here corresponds to that point on the green curve, and the second point on the blue curve corresponds to the second point on the green curve, and so on. And we can say that the green curve is more optimal compared to the blue curve with respect to the trade-off between the error rates, because the optimal point would lie somewhere here. It is the bottom left corner of the rectangle spanned by the base decision rule and the maximum likelihood decision rule. And the green curve is below that blue curve and therefore also closer to our optimal point. And just to put into a punchline, we have a little drop in the mean IU by 0.4%, but we are able to reduce the number of false negatives by more than 1/3, from 900 to, let's say, 550. Here is a demonstration how MetaFusion performs on the cityscapes dataset. In the top row, we see differently predicted segmentation masks obtained by applying the base decision rule, the maximum likelihood decision rule, and MetaFusion. In the bottom row, we see the original image and the corresponding ground truth. In general, the neural network we use for this task performs quite well on the dataset, so there are only a few human instances that are completely overlooked in this dataset. Therefore, the set of candidate segments for MetaFusion is very small, and we have to look closely to see some results. And we have to look into these small regions here. What we observe is that base completely overlooks human instances that are labeled in the ground truth. With maximum likelihood, we find them. Additionally, it also says that there are some humans here on top of this building, and we can get rid of them, these false positives, by applying MetaFusion. And this is a very desirable effect. We get this effect with only computational overhead, as MetaFusion is a pure post-processing tool that only further processes the softmax output of a neural network. For the classification task, we apply a simple boosting algorithm, and compared to deep learning models, in particular to deep learning models for semantic segmentation, the computational cost is very cheap and can be neglected. And that was how we perform controlled false negative reduction in semantic segmentation with our method that we term MetaFusion. The audience, thank you for listening. If you have any questions, remarks, or ideas, feel free to reach out. And like most of you, I also would prefer to be in Glasgow right now. At this point, we have to thank the WCCI organizers for making this event still possible. Thank you.